Hi everyone, my name is Amna and welcome to Mind and Maths. I created this space for us to explore mathematics and economics gently, slowly, and with real understanding without any stress or pressure. Before we begin today's lesson, just a small note. This is my very first YouTube video. I'm currently recovering from a very sore throat, and English is not my first language. So, thank you for being patient with me. All right, let's begin. So before I discuss the role of that total derivatives play in helping us find multipliers in the ISLM framework, I just want to give a brief introduction to what and how we calculate the total derivative. So let's start with just a simple example. Let's say a variable y depends on, that is a function of, a variable x, a variable r, and a variable z. Since f depends on three variables, therefore whenever we take the derivative of f with respect to x or r or z, it's going to be a partial derivative. Okay, so if I want to see the change in y dy, then firstly I'm going to take the partial derivative of f with respect to x and multiply by dx. Then then comes the second variable, which is r. We take the derivative of a partial derivative of f with respect to r multiplied by change in r plus partial derivative of f with respect to z and multiply it with change in z. So basically y is the same as the function f. You can imagine as if this is being cut off and you're just left with the change in f, which basically is the change in y. That's how I kind of do my rote learning. Another way we can express this is I like this terminology of writing f and x in the subscript to denote the partial derivative. So fx dx, fr in the subscript dr, plus fz in the subscript dz. Okay, so let's take just one more example and let's make it slightly complicated. Let's say y depends on, again, three variables. So it's again a function of x, r, and z. But this time x depends on a variable t, while r depends on a variable m, and z depends on a variable q. So how do we take the total derivative now? Remember, since there are three variables again, so there I'm going to be adding three times the and yeah, so they all depend on just one variable, so there's just going to be three terms that are going to be added. So let's begin. I'm going to have the dy on the left side, which is change in y. Now again the partial derivative of f with respect to x. Now x depends on t, so, and it only depends on t, so now we don't need a partial derivative. So we're just going to write dx by dt, and I'm going to multiply it by dt because all I want to remain is df. So I'm just going to imagine as if these two things get cut off and change in t gets cut off. So I'm left with change in f only. Then comes the next variable's turn. So I'm going to take the partial derivative of f with respect to r, then r with respect to m because r depends on m, and dm. Similarly, the last is the variable z. So it's going to be the partial derivative of f with respect to z, dz by dq into dq. So we can write this same expression as follows. The derivative of f with respect to x, and we can write this x, the derivative of x with respect to t, and dt, plus, or we can, I guess we can also just write it like this. Maybe this would be better, xt. Maybe we can just leave it like this, dx by dt dt plus df, sorry, f r r by dm dm fz dz by dq. Anyhow, so why do we need to learn how to calculate the total derivative? The answer to that is that in economics, we're very much interested in how to calculate the government spending multiplier, government spending multiplier, which is basically the change in output or GDP because of a change in government spending. We are also interested in the money multiplier. So we basically are interested in any impact on output that a change in money supply can have. So what we're interested is that we're interested in the impact of government spending and money supply on GDP. So that's our main concern. So let's start by analyzing the goods market. So in the goods market, we know that equilibrium holds whenever aggregate demand is equal to aggregate supply. We know aggregate demand equals C plus I plus G in a closed economy with government, and aggregate supply equals output. So if I write it like this, that output is a function of consumption and it is a function of investment and it is a function of government spending. And what is the relationship? C plus I plus a G. However, we do know that, for instance, C depends on your disposable income. So for instance, C is a function of income. What about the level of investment? Level of investment, we can say, depends on the interest rate. What about government spending? Government spending depends on output as well, but here, for simplicity, we can assume that it's exogenously set. Okay, we can see that the partial derivative of f with respect to c is just 1, and the partial derivative of f with respect to I is just a 1, and partial derivative of g with respect excuse me, and the partial derivative of f with respect to g is also 1. Okay, so let's start by taking the total derivative now of this equation. So change in y is basically the partial derivative of f with respect to c with respect to y into dy plus the partial derivative of f with respect to I, the derivative of I with respect to an r into dr plus partial derivative of f with respect to g dg. since this is equals to 1, this is equals to 1, and this is equals to 1, this whole equation collapses to the following. Yeah, here we go. Looks nicer. To make our equation even more compact, we can write this as the derivative of c with respect to y, dy, plus derivative of r with I with respect to r, dr plus dg. Now at this point, what I need to know is how to distinguish exogenous variables to endogenous variables. Remember, all variables that are determined within the model are endogenous. So as you can see, you have interest rate and output on the axis. So therefore, we have output and interest rate as endogenous variables. And since consumption depends on output, if this is a endogenous variable, so will consumption be. And since investment depends on interest rate, if interest rate is endogenous, so will investment. So besides output and interest rate, we have two other endogenous variables, which are C and I. What about exogenous variables? So in this equation, only government spending is the exogenous variable, but when we introduce the money market, the money supply will also be taken as fixed. So we'll be assuming a monetary targeting central bank with a vertical money supply curve. So therefore, we're going to assume money supply as being exogenously set. What about parameters? We'll introduce parameters in a bit. For that, we'll have to state the functional forms of these the consumption function and investment function. We'll do that in a bit. Okay, so I want all the endogenous variables to be on the left hand side. So let's do that. I'm going to have 1 minus cy into dy minus IR dr is equals to dg. This is basically my first equation. If the question, suppose we have given the consumption function as equals to autonomous consumption plus marginal propensity to consume, and we're going to take out the tax. Let's assume a proportional tax. Let's take the tax rate as k and multiply it by y. So over here we can see, if I want to take the derivative of c with respect to y, it is b1 minus k. And since marginal propensity to consume is between 1 and 0 and the tax rate is between 1 and 0, therefore this expression is going to be also going to be between 1 and 0. Therefore, the derivative of c with respect to y is going to be between 1 and 0. What about the investment function? Let's suppose the investment function looks like this. I naught minus AR. What is the derivative of investment with respect to R? It is a minus A. This is basically negative since A is a positive parameter. So in conclusion, we can see that over here we can see that the derivative of I with respect to R is negative, and over here we can see that the derivative of consumption with respect to income lies between 1 and 0. What are the parameters then? So the parameters are P, K, A. It's quite useful to know how to distinguish between um, endogenous and exogenous variables and what parameters are, especially when you want to put your data in Dynair and MATLAB. So it's a good skill to know. Okay, coming back to this equation which we've written down. Suppose I say that there's no change in government spending, right? So there's no change in government spending. What does this collapse to? This becomes IR dr is equals to 1 minus cy into dy. So dr over dy is 1 minus cy over IR. As you can see, the numerator here is actually a positive number and the denominator is a negative number. So therefore the quotient is going to be negative. What does this mean? This means that we have a negatively sloped IS curve. Yeah. So let's move on now to the money market. In the money market, we know equilibrium happens when the demand for money equals the supply of money. So what is the demand for money? Demand of money is a function of output and interest rate. Sometimes we can write it like this: h0 plus h1y minus h2r, for instance. The partial derivative of L with respect to y is written as this sometimes. Partial derivative with respect to y is h1, which is a positive number, and the partial derivative with respect to r, written like this, is a minus h2, which is a negative number. So we can conclude whenever we see derivative of L with respect to y, we know it's a positive number, while whenever we see L R, we know it's a negative number. Okay, moving on. We want money supply, M over P, real money balances, to be equals to money demand. Now let's take the derivative on both sides. So change in money supply will be equals to the partial derivative of L with respect to y dy plus partial derivative of L with respect to r into dr. Therefore, we have Ly dy plus Lr dr, and here we have change in money supply. Remember, I want all my endogenous variables on the left hand side, so I basically want to write this on the left side, and I want this on my right side and that on my left side. Yeah, so this right here is my equation 2. Okay, so if I assume that there's no change in monetary policy, so I can say there's no change in monetary policy. So therefore, if there's no change in monetary policy, I'm basically looking at a movement along the LM curve, right? Because any change in policy causes a shift. Similarly, before, when we said there's no change in government spending, basically this ensures that we are going to be moving along the IS. because any change in government spending or government spending policy will actually shift the curve. So, okay, coming back to here, when we put this in equation 2, we get LR dr equals to minus Ly dy. So therefore dr over dy is equals to minus Ly over Lr. Since the numerator over here is positive, denominator is negative, so a minus into a minus will give us a positive number. What this means is that we have a positively sloped LM curve. Okay, so now we have two equations, and we have two unknowns and two equations. So therefore we can convert the model into matrix form, and we'll have a 2 by 2 system. So let's put these two equations in matrix form. So what were the two equations? Let's scroll up. This was my first equation. And this was my second equation. Converting this into a 2 by 2 system is fairly easy. I know the coefficient of dy is 1 minus cy. Coefficient of dr is minus ir. Coefficient of dy is ly. Coefficient of dr is lr. We're going to multiply it by the column which contains dy and dr. I'm going to equal this to the column dg dm over p. Voila, this is the matrix form. So at this point, you can recognize that this is basically an ax is equals to b system, where you have a 2 by 2 matrix which is being multiplied by a column vector which is 2 by 1. Therefore you have resulting column vector which is a 2 by 1 vector, and you can either solve this system by taking the inverse of matrix A and multiplying it with the vector B, or you could basically use Gaussian elimination by using row operations. And the third option, which I'm going to go for right now, is the Cramer's rule. I find the Cramer's rule quite efficient. For that, I need firstly the determinant of matrix A. So the determinant of matrix A is the determinant of 1 minus cy minus 1 r ly lr. So when I take the determinant, I get lr 1 minus cy plus ly ir. So this expression right here is a positive number. This right here is a negative number. This is a negative number, and this is a positive number. So this whole thing is going to be negative. This whole thing is going to be a negative. Therefore, the whole determinant is a negative number. If anybody finds this confusing, what they can do is that they can actually substitute in the values of these that the functional forms give us. So for instance, LR was a minus H2, and CY was a B1 minus K, and LY was an H1, and IR was a minus A. So in this context, we can basically show that you can take the minus out and leave the rest as it is. And you can show that this is negative because you are adding two positive uh, uh, real numbers. So therefore, when you multiply it with a negative number, you're going to have a determinant which is less than 0. Okay, so now let's do the fun part. I want to see the value of dy and then I want to see the value of dr. So moving forward, let's find the value of dy. I know for dy, since it's in the first, it's the first entry of the column vector. So I'm going to replace the first column with the column b. The second column is going to remain the same. Actually, I need the determinant. Now taking the determinant of this matrix, I'm going to get a LRDG plus IRDMP over the determinant of matrix A. Okay, and if I want to find dr, it's going to be the determinant of 1 minus cy ly, which remains there, and now I'm going to replace the second column with the column b, like this. Now I'm going to take the determinant, which is going to be 1 minus cy dmp minus ly dg over the determinant of the matrix. Okay, now we have all we need, all the information that we need in order to find the multipliers. So let's just write this here as a conclusion, and let's write this down here as our other conclusion, because it's kind of nice to have all the conclusions written together. So this is our conclusion box. Here it is. Okay, so now I want to see the impact of fiscal policy and monetary policy on output and interest rates. So let's just divide the page into halves so we can compare. So let's analyze fiscal policy here. So therefore what I'm saying that there's no change in monetary policy. I just want to see fiscal policy. So what does this equation collapse to? If this is my equation, what does it become? So I don't have this expression here becomes a 0. So therefore we are left with LRDG over the determinant of matrix A. So we have dy by dg is equals to LR, which is a negative number, and in the denominator we again have a negative number, therefore this is a positive number. What this means is a positive relationship between government spending and output. So a rise in government spending should lead to a rise in output as expected. Let's see the impact of monetary policy, monetary expansion even, when it comes on output, right? So again, we're interested to see what happens when there's a rise in monetary policy. So we want to make the claim that there's no change in government spending. So the IS curve shift here. What does this collapse to? This becomes IR dmt over the determinant of matrix A. So the change in output because of a change in monetary policy is IR, which is a negative number, and the denominator is also a negative number. Therefore, the quotient will be a positive number. This shows that there's a positive relationship between money supply and output. It's kind of cool. Let's just see the impact on interest rate before we wrap things up. This was the equation for the change in interest rate. Let's copy this down and analyze the impact of fiscal and monetary policy. So we have this right here, we have this right here. Okay, we're all set. So dr is equals to this, dr is equals to this. On the left side, there's no change in monetary policy, so we are left with minus ly dg over the main determinant. Therefore, dr over dg, change in interest rate because of a change in government spending, is minus ly over the determinant. So this is going to be positive. Since ly is a positive number, this is a negative number. Negative into a negative will make a positive. So what this means is that if there's a rise in government spending, it should lead to a rise in the interest rate. If we make a diagram for this, knowing that there is output on the y-axis and interest rate on the x-axis, and we make an IS curve and an LM curve, and we say this is the initial IS curve, this is the initial LM curve, we'll probably need another diagram on the right side as well, so I'm just going to take this here as well. So let's see, we were analyzing the impact of a fiscal expansion, so IS should move right here, and we said that interest rate and output should rise. And yes, that does overlap and tally with our diagram as well. So a fiscal expansion leads to an increase in output and an increase in the interest rate. Okay, coming back to the monetary policy, this is, we're going to plug in dg is equals to 0 here. So we're left with 1 minus cy, change in money supply, over the determinant of matrix A, and we're left with change in interest rate because of a change in money supply, and we're left with the a numerator which is positive and a denominator which is negative. Therefore, we have a negative relationship, which means a rise in money supply should actually lead to a fall in the interest rate. So if we draw it over here, it's going to go like this. So monetary expansion is going to shift the curve here, and we're going to end up at point B over here as well, at point B from point A, and we can see the impact on output. Oh, sorry, that was point A. So the impact on output you can see is positive, and the impact on the interest rate you can see as negative, which we can also, if we want, we can show by these arrows. So that brings about the end of this lecture. I hope you guys enjoyed it. I hope it wasn't boring, and this was my first ever video for YouTube, so I hope it went okay. I'm going to just put in the link for these notes on the video, which are going to be for free, available for free. If I made any mistakes, please feel free to comment below and let me know, and I'll make the corrections. Thank you. Bye.